Question number 14. The point of maximum entropy on a Fano curve in a temperature entropy Ts diagram represents the option A maximum flow Mach number, option B minimum flow Mach number, option C sonic Mach number, option D normal shock in the flow. Right? They are asking about the point of maximum entropy. So in class we derived the relations for Fano flow, right, and we also plotted the graph. So here I will not be using any derivation. It is straightforward question for 1 mark. So after all the derivations and conclusion, we also made one table, correct, for Rayleigh flow and Fano flow. Even if you just remember that table discussed in the class, you can still do this. We studied HS diagram in the class, right, enthalpy entropy diagram, and curve was like this, correct, for Fano flow. This is the point of maximum entropy, and what was the Mach number we got here? I am not doing the derivation, we already did in the class, that is Mach number is equal to 1, means sonic Mach number, correct. They are asking on Ts diagram, so enthalpy is nothing but H is equal to Cp into T. Cp is constant, so it is Ts diagram also, right. So maximum entropy on Fano curve in Ts diagram represent sonic Mach number. So option C, right. This was straightforward 1 mark question. Even if you just remember the table drawn in the class, you can still do this. Question number 15. Consider a two-dimensional potential flow over a cylinder. If the free stream speed is u infinity, the maximum speed on this cylinder surface is. So for cylinder, this is the cross-sectional view, circular. So flow will be like this. So for cylinder, we know that velocity Vr, relative velocity is 0, and V theta is given by minus u infinity sine theta bracket 1 plus capital R square upon small r square, right. So they are asking on the cylinder surface. So for surface, small r is equal to capital R, because capital R is the radius of cylinder. So V theta will be equal to minus 2 u infinity sine theta. Now when V theta will be maximum? When this sine theta will take maximum value, right. So this is the angle theta. So at pi by 2 here on the top of the cylinder, sine theta will be 1. So at that position, V theta will be equal to, from this formula, minus 2 u infinity, minus sign is just for direction, and at theta is equal to 3 pi by 2. 3 pi by 2, sine theta will be minus 1. So at this point, at the bottom, V theta will be equal to 2 times of u infinity. So this is the known result only, that maximum velocity on the cylinder surface is 2 times of free stream velocity, right. Free stream is u infinity. So option C. Question number 16. Consider study two-dimensional incompressible flow over non-porous flat plate as shown in the figure. For the control volume PQRS, so PQRS, the speed u infinity at section PQ is uniform. So it is entering from this side at uniform speed u infinity, and the speed at this section RS is given by, so they have given the expression u is equal to a naught y by h raised to n, correct. where n is a positive integer, the value of A naught for which flow through the section PS will vanish. Means from here to here, the section PS means mass flow through this should be 0. Means whatever is coming from this side, it has to go from this side. Correct? It means the mass flow rate entering from this side is equal to exit from this side. Correct? What is the mass flow rate entering from left side at section PQ? Mass flow rate is rho A V, means rho velocity u infinity and area is this height, it is h, and width perpendicular to the screen. Let's say the width perpendicular to the screen is b, so area will be b into h. So this is the mass flow rate entering from left side from the section PQ. Right? Now what will be the mass flow rate through the section SR? For this, let's take one small strip like this. Its thickness is dy. So what will be its area? B into dy. Correct? What will be the mass flow rate? Velocity into area into density. Correct? So rho into area into velocity, that is u. That will be the mass flow rate through this small strip. If we want to find out total mass flow rate passing through this section SR, we have to integrate it from 0 to h, because this height is h here. Right? So this mass flow rate is equal to rho, we can take common because it is incompressible. So rho is constant, b is also constant, width perpendicular to this screen. Correct? Integration u dy 0 to h. Correct? These two mass flow rates should be equal, means rho u infinity b h is equal to rho b integration 0 to h. What is the expression for u? We can substitute. That is a naught y by h power raised to n dy. Right? Rho u infinity bh is equal to rho b. A naught is constant, so we can take a naught outside of the integration. A naught and h raised to n, it is also constant. Integration 0 to h y raised to n dy will be equal to rho b a naught upon h raised to n. Integration of y raised to n will be y power n plus 1 upon n plus 1. Right? Limit 0 to h. So we can write rho u infinity b into h is equal to rho b a naught upon h raised to n into n plus 1. We can apply the limit, so it will be h raised to n plus 1. Right? Rho and rho will get cancelled out, b and b will get cancelled out. Correct? So this h raised to n we can take to that side. U infinity into h raised to n will become h raised to n plus 1 is equal to a naught upon n plus 1 into h raised to n plus 1. This will get cancelled out. So a naught will be equal to u infinity n plus 1. Right? B option. So in question itself they have given the hint that value of A naught for which flow through the section PS will vanish. So whatever mass flow rate is coming from this side, it has to go from that side. Correct? Mass flow rate from this side will be 0. Question number 17. Consider the velocity distribution of U shown in the figure for two adjacent fluid layer L1 and L2. The viscous force exerted by L1 on L2 is. So here this is L1, this is L2. Two layers are given. Option A to the right, option B to the left, option C vertically upward, option D vertically downward. So force exerted by viscous force will not be in vertical direction, correct? So C and D are incorrect option. Now whether it is to the right or the left, so moment is in this direction, viscous force always opposes the motion, correct? So it means the viscous force exerted by L1 on L2 is toward left hand side. So option B. Question number 25. Across an oblique shock wave in a calorifically perfect gas. So in option they are asking about stagnation enthalpy, stagnation entropy, stagnation temperature and speed of sound. Now we already know that across the oblique shock total temperature remains constant because it is adiabatic. It is not isentropic but it is still adiabatic, correct? So it means stagnation temperature T0 is constant, correct? And what about static temperature? It increases, correct? Static temperature will increase. So if we multiply T0 with Cp, it will become stagnation enthalpy. So H0, Cp is also a constant, so H0 is also constant. So stagnation enthalpy is constant. Here in option A, they are telling that stagnation enthalpy changes, which is wrong. In option C, stagnation temperature changes, which is also wrong because stagnation temperature remains constant, correct? Now, in option D, speed of sound changes. We know that speed of sound depends upon static temperature. So, A is equal to under root gamma RT. So temperature is increasing, so speed of sound will also increase, correct? So this is correct option. The speed of sound changes, right? Now about option B, the stagnation entropy changes. So formula for stagnation entropy, delta S is equal to Cp ln T02 by T01 minus R ln P02 by P01, right? So as we already know, stagnation temperature remains constant, so this will be 1 T02 by T01, ln1 is 0, right? Minus R ln P02 by P01. Now we also know that P02 is less than P01. It means delta S will be greater than 0 because this quantity will be positive, correct? So stagnation entropy changes. So both B and D are correct option. Question number 26. NACA 2412 aerofoil has, so it is 4-digit series. So for 4-digit series, NACA 2412. So for 4-digit series, we know that last two digit gives us maximum thickness in terms of the percentage of cord. So 12% maximum thickness. It is 12% of cord, correct? First digit gives us maximum camber. So 2% is the maximum camber, 2% of chord. Second digit, this digit gives us location of maximum camber in tens of chord. So if we multiply 4 by 10, it will be 40. So location of maximum camber is 40% of the chord at 40% of the chord from leading edge, correct? So in option A, 4% maximum camber with respect to the chord. So it is wrong because maximum camber is 2%, correct? Maximum camber at 40% of chord. So it is correct. C option, 12% maximum thickness to the chord. So it is also correct. Here we got maximum camber at 20% of the chord. No, it is at 40%, and we have already selected this. So both B and C are correct answer. Question number 39. A cylindrical object of diameter 900 mm is designed to move axially in air at 60 meter per second. Its drag is estimated on a geometrically half-scale model in water. So prototype was moving in the air with the speed of 60 meter per second. Now its drag is estimated on geometrically half-scale model in water and not air. In water, assuming flow similarity. Coefficient of dynamic viscosity and densities for air and water are 1.86 into 10 to the power minus 5 Pascal second, 1.2 kilogram per meter cube, and 1.01 into 10 to the power minus 3 Pascal second and 1000 kilogram per meter cube respectively. Drag measured for the model is 2280 Newton. Drag experienced by the full scale object is in Newton. So diameter of prototype is 900 mm, that is 0.9 meter. Velocity 60 meter per second. Density and viscosities are given for air and water, and the drag on the model in the water is 2280 Newton. So here viscous force is dominating, right? So for dynamic similarity, Reynolds number should be same. So Reynolds number for prototype in air should be equal to Reynolds number for model in water, correct? So rho V d upon mu, this is for air, is equal to Reynolds number rho V d upon mu for water. So let's substitute the values and let's find out velocity of the model in water. So rho, that is 1.2 into velocity 60 into 0.9 meter upon 1.86 into 10 to the power minus 5 is equal to 1000 into velocity into diameter, that is half scale model, so 0.45 meter upon 1.01 into 10 to the power minus 3. So velocity of model in water is equal to 7.82 meter per second. Now we know that drag is proportional to rho v square into surface area. So ratio of drag, that is drag on prototype in air upon drag on model in water is equal to rho, that is 1.2 into V square into area. So it is moving axially, so this will be the area, this, correct. So this is pi by 4 d square 0.9 square upon 1000 into 7.82 square, velocity just now we got, into pi by 4 into 0.45 square. This will get cancelled out. So drag on the model in water is known, it is given 2280. So drag on prototype in air is equal to 644 Newton. So in option B, 644 Newton. Question number 44. A convergent nozzle fed from a constant pressure, constant temperature reservoir is discharging air to atmosphere at 1 bar absolute with choked flow at the exit marked as Q. So here the flow is choked and reservoir pressure and temperature is constant. Flow through the nozzle can be assumed to be isentropic if the exit area of the nozzle is increased while all the reservoir parameters and ambient conditions remain same. Then at steady state, option A, nozzle will remain choked. Option B, the nozzle will be unchoked. Option C, the Mach number at section P will increase. Option D, the Mach number at section P will decrease. So there were number of such type of questions in the test series, in full length mock test, in subject wise test, and even in topic wise test, that is 1D flow test level 1 and level 2. Both the tests had number of questions where we are changing all the parameter for choked flow, like changing the area, changing reservoir pressure, changing reservoir temperature, changing exit pressure, right? There were number of such questions in the test series. So here what they are telling, the reservoir pressure and temperature will be constant, right? So for choked flow, we know that what is the pressure ratio, P naught by P star, that is equal to gamma plus 1 by 2 power raised to gamma upon gamma minus 1. So if we put gamma is equal to 1.4 for the air, we will get P naught by P star is equal to 1.89. Means stagnation pressure of the tank should be at least 1.89 times of the exit pressure, then only it will be choked. If pressure ratio is more than this, then still exit pressure will be P star only and it will be choked. So initially they are telling that it was choked flow at the exit marked as Q. Now we are changing the area, but they are telling that all the reservoir parameters and ambient conditions remain same, correct? So whatever pressure ratio on which it was working, now also pressure ratio is same. So obviously it will be choked only, correct? Because pressure ratio is same. So first thing is clear that nozzle will remain choked. So in option A, nozzle will remain choked. Now they are also asking about the Mach number at section P, right? It will increase or decrease. In class we also derived the mass flow rate for choked convergent nozzle, right? So I'm not going to write complete equation, but from that formula we came to know that mass flow rate for choked convergent nozzle is directly proportional to P naught A star throat area and inversely proportional to square root of stagnation temperature of the tank, correct? Now here this A star is increasing because we are increasing the area here, and new area will be again A star only because in second case also it is choked, correct? So we are increasing the area, means mass flow rate will increase. Now mass flow rate will be more than the earlier case. It means this section, this P section has to pass more mass flow rate. So obviously here velocity and Mach number should increase, right? So in option C, Mach number at the section P will increase, right? Question number 50. A rotational velocity field in an airflow is given as, velocity vector is given with A is equal to 10 per second, B is equal to 20 per second. The air density is 1 kilogram per meter cube and the pressure at XY location, means 0 meter, 0 meter is 100 kPa. Neglecting the gravity, the pressure at x, y is equal to 6 meter, 8 meter is in kPa. So this is the boundary condition they have given. So velocity vector V is equal to Ay plus Bxj. So A is equal to 10 and B is equal to 20. Let's substitute. Velocity vector will be equal to 10y I cap plus 20x j cap. And what is velocity vector in 2D? V is equal to u I cap plus v j cap, where u is the velocity in x direction and this small v is the velocity in y direction. So u is equal to 10y after comparing and v is equal to 20x, right? And time is not involved here, so it is steady flow, right? Now in class we have studied about momentum equation in x direction, y direction, z direction, that is differential form of momentum equation. So let's write the momentum equation in x direction. So in class we have studied in 3D, here we will be writing in 2D only because given problem belongs to 2D flow. So what was differential form of momentum equation in x direction? Dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to minus 1 upon rho dou p by dou x plus mu by rho bracket dou square u by dou x square plus dou square u by dou y square, right? Here we have neglected the body forces, means gravity. And what is this term? That is acceleration in x direction, right? In lecture we saw this. This is the easy way to remember that left hand side is acceleration in x direction. Now for steady flow, this term is 0. What about dou u by dou x? Dou u by dou x, u is not a function of x here, so 0. Dou square u by dou x square, 0. What about dou u by dou y? That will be 10, and dou square u by dou y square, that is equal to 0. Means this is 0, this part also 0. Dou u by dou x, this is 0. So we can write this thing, v into dou u by dou x, v is 20x. So 20x into dou u by dou x, that is 10, is equal to minus 1 upon rho dou p by dou x, correct? So from here dou p by dou x is equal to minus 200 into rho into x. If we integrate this, we will get p is equal to minus 200 rho x square by 2 plus some constant. So P is equal to minus 100 rho x square plus some constant. Similarly, we can write the differential form of momentum equation in y direction also. So what was that? Dou v by dou t plus u dou v by dou x plus v dou v by dou y is equal to minus 1 upon rho dou p by dou y plus mu by rho bracket dou square v by dou x square plus dou square v by dou y square, right? Again, for steady flow, this will be 0, right? And this entire term is a y, acceleration in y direction. So what is the expression for v? V is equal to 20x. So v is equal to 20x. What about dou v by dou x? That is 20. Dou square v by dou x square is equal to 0. Dou v by dou y is 0 because v is not a function of y. Dou square v by dou y square is equal to 0. So again this term is 0, this term is also 0, and dou v by dou y, this is 0. So we have u into dou v by dou x. So u is 10y into dou v by dou x, that is 20, is equal to minus 1 upon rho dou p by dou y. From here we can write dou p by dou y is equal to minus 200 rho into y. Upon integrating, we can write p is equal to minus 200 rho y square by 2 plus some constant. So we got p is equal to minus 100 rho y square plus some constant. So this is in y, and in x we already got. Let's add that. So p is equal to minus 100 rho x square plus y square plus another constant c, right? Now here we need the boundary condition. That's why they have given this condition, that pressure at x comma y 0 meter comma 0 meter is 100 kPa. Now this boundary condition is needed. So pressure is 100 kPa, 100 into 10 to the power 3 is equal to minus 100, density is 1 and x is 0. So y is also 0 plus constant. So this term is 0. So c is equal to 100 into 10 to the power 3. So this expression P is equal to minus 100 rho x square plus y square plus constant, that is 100 into 10 to the power 3. Now we can find out pressure at any location. So where they are asking? At x is equal to 6 meter and y is equal to 8 meter. So let's substitute. P is equal to minus 100, rho is 1 kilogram per meter cube, x is equal to 6, so 6 raised to 2, 36, y is equal to 8 raised to 2, 64 plus 100 into 10 raised to power 3. So this will be minus 100, 36 plus 64, 100 into 10 raised to power 3. So this will be minus 10 into 10 raised to power 3 plus 100 into 10 raised to power 3, means 90 into 10 raised to power 3 Pascal. So they are asking in kPa, right? In kPa, it will simply be equal to 90 kilopascal, right? Question number 51. Consider a circular distribution over a finite wing given by the equation below. So they have given circulation expression. The wingspan B is 10 meter. Maximum circulation gamma naught is 20 meters square per second. Density of air is 1.2 kilogram per meter cube and the free stream speed is 80 meter per second. The lift over the wing is in Newton we have to find out. So this is the expression for circulation gamma. Now we know that lift is equal to rho free stream velocity V infinity integration of gamma over span. So we can substitute the value of gamma circulation and we can integrate it over the span. So gamma is equal to gamma naught 1 minus 2y by b if y is greater than equal to 0 and less than equal to b by 2, and if y is greater than equal to minus b by 2 and less than equal to 0, then it is given by gamma naught 1 plus 2y by b. So total span is b, that is equal to 10 meter. This is y is equal to 0 minus b by 2 plus b by 2. So let's substitute and integrate. So lift is equal to rho V infinity bracket integration minus b by 2 to 0. For this expression is this gamma naught 1 plus 2y by b dy plus integration 0 to b by 2. Gamma naught 1 minus 2y by b dy bracket close. So for 0 to by, this is the expression for gamma circulation. So gamma naught we can take common. So lift is equal to rho V infinity gamma naught bracket integration minus b by 2 to 0 1 plus 2y by b dy plus integration 0 to b by 2 bracket 1 minus 2y by b dy bracket close. So lift is equal to rho V infinity gamma naught bracket integration of 1 is y plus y square by 2. So 2 and 2 will get cancelled out. So it will be y square by b limit minus b by 2 to 0 plus integration of 1 again y minus y square by b limit 0 to b by 2 bracket close. So let's put the limit. L is equal to rho v infinity gamma naught upper limit minus lower limit. So upper limit is 0, so it will be 0 minus lower limit minus b by 2 plus b square upon 4b plus again upper limit is b by 2, so b by 2 minus b square by 4b minus lower limit, that is 0. So this will get cancel out. So we will get rho v infinity gamma naught bracket b by 2 minus b by 4 plus b by 2 minus b by 4. So b by 2 and b by 2 will be b by 2 plus b by 2 b, and minus b by 4 and this minus b by 4. So minus b by 2. So b minus b by 2 is b by 2. So lift is equal to rho v infinity gamma naught into b by 2. Now we can substitute the values. B is 10 meter. Maximum circulation gamma naught is 20 meter square per second. Density of air is 1.2 kg per meter cube. Free stream velocity v infinity is 80 meter per second. So density 1.2 into free stream velocity 80 into maximum value of circulation 20, b is 10 by 2, lift is equal to 9600 Newton, right? Question number 52. Consider a solid cylinder housed inside another cylinder as shown in the figure. The radius of inner cylinder is 1 meter and its height is 2 meter. The gap between the cylinder is 5 mm. So this gap they have given, it is 5 mm, and it is filled with a fluid of viscosity 10 raised to power minus 4 Pascal second. The inner cylinder is rotating at a constant angular speed of 5 radian per second. So they have given omega 5 radian per second. Radius of inner cylinder r is equal to 1 meter and its height is 2 meter. While the outer cylinder is stationary. So outer is stationary, inner is rotating. Friction at the bottom surface can be ignored. Velocity profile in the vertical gap between the cylinder can be assumed to be linear. The driving moment required for the rotating motion of the inner cylinder is in Newton meter. And if you remember that this type of problem was given in the homework after lecture 1 and lecture 2 of fluid mechanics, right? So the driving moment, the torque, will be equal to torque is equal to viscous force into radius of cylinder r, right? Force into perpendicular distance. What will be viscous force? Shear stress into area. Shear stress we can write mu dou u by dou y from Newton's law of viscosity into area, right? What will be the area of this cylinder? 2 pi r h. So torque we can write shear stress mu dou u by dou y into area, that is 2 pi r h into r. So this is the amount of torque needed, right? So how we can find out velocity gradient? Dou u by dou y. So first of all, u, velocity, tangential velocity of this cylinder at this outer point, this will be omega into r. So 5 into 1, that is 5 meter per second. What will be dou u by dou y? 5 minus 0 upon the gap. The gap is 5 mm they have given. So 5 into 10 raised to power minus 3, right? So it will be 10 raised to power 3 per second. Correct? Now we can substitute torque is equal to mu, that is here 10 raised to power minus 4 Pascal second, 10 raised to power minus 4 into 10 raised to 3 into 2 pi rh. 2 pi, r is 1, h is 2 into 1. So it will be 0.4 pi, that is equal to 1.256 Newton meter. Right, so this much amount of torque is needed, means driving moment, rounded off to 2 decimal place. So torque is equal to 1.26 Newton meter. Right, this will be the amount of driving moment required for the rotating motion of the inner cylinder. Question number 53. In a converging duct, area and velocity at section P are 1 meter square and 15 meter per second respectively. The temperature of the fluid is 300 Kelvin. Air flows through the nozzle can be assumed to be inviscid and isothermal. So this side temperature is 300 Kelvin and here also temperature is 300 Kelvin. Characteristic gas constant is 287 joule per kilogram Kelvin and ratio of specific heats is 1.4 for air. To ensure that airflow remains incompressible, Mach number less than equal to 0.3 in the duct, the minimum area required at this section Q is in meter square. So we have the condition that Mach number at the exit should be less than equal to 0.3. What is Mach number? V by A, right? That is V upon under root gamma r t. So velocity V at the exit will be equal to 0.3 into under root 1.4 287 into 300. So velocity V is equal to 104.156 meter per second. Now we have the velocity. Now we can apply the continuity equation between these 2 points P and Q. So using continuity equation we can write mass flow rate rho A V at section P is equal to rho A V at section Q. Since it is incompressible, so density can be assumed to be constant. So we can write AP velocity at point P is equal to AQ into VQ. Area at section P is 1 meter square, so 1 into velocity 15 meter per second is equal to AQ we have to find out into VQ, that is 104.156. So AQ is equal to 15 by 104.156, that is equal to 0.14 meter square. So this will be the area at Q, 0.14 meter square. Question number 54. Consider thin symmetrical airfoil at 2° angle of attack in uniform flow at 50 meter per second. The pitching moment coefficient about its leading edge is rounded off to 3 decimal place, right? In class we have derived formula for pitching moment coefficient about various point for thin symmetrical airfoil like leading edge, quarter chord point, trailing edge, right? So what was the formula for pitching moment coefficient about leading edge? Cm leading edge is equal to minus pi alpha by 2, right? So it will be minus pi by 2 alpha in radian. So alpha is 2°. So 2 into pi by 180. So it is minus pi square by 180, which is equal to minus 0.0548. So rounded off to 3 decimal place. So moment coefficient about leading edge is equal to minus 0.055, right? Question number 55. A convergent divergent nozzle with adiabatic walls is designed for an exit Mach number of 2.3. It is discharging air to atmosphere under the conditions indicated in the figure, where there is a formation of expansion wave at the exit. Flow through the nozzle is envisaged. The characteristic gas constant for air is 287 joule per kilogram Kelvin. Gamma is equal to 1.4. When the reservoir pressure is 25 bar absolute and the temperature is 300 Kelvin, Prandtl-Meyer expansion waves appear at the nozzle exit as shown. The minimum percentage change in the reservoir pressure required to eliminate the wave system at the nozzle exit under steady state is in percentage. So at 25 bar there is a formation of expansion wave at the exit, right? So we have to eliminate this, means it should be perfectly expanded according to design condition. So design Mach number is 2.3 given. So we have relation between stagnation pressure of the reservoir P0 and exit pressure P0 by P is equal to 1 plus gamma minus 1 upon 2 m square power raised to gamma upon gamma minus 1, right? This is the isentropic relation between stagnation and static pressure and Mach number. So it is designed for Mach number equal to 2.3. So ambient pressure is 1 bar absolute. So if we have to eliminate the expansion wave, it should be perfectly expanded up to back pressure, that is ambient pressure of 1 bar. So P is equal to 1 bar. We have to find out P0 by P is 1 bar is equal to 1 plus gamma is 1.4, 1.4 minus 1 upon 2 into 2.3 square power raised to gamma upon gamma minus 1. So we will get P naught is equal to 12.5 bar. Right? If reservoir pressure will be 12.5 bar here, then it will be perfectly expanded and there will not be any expansion wave at the exit. Correct? So they are asking percentage change. So initially it was 25 bar here, now it is 12.5. So percentage change will be equal to 25 minus 12.5 upon 25 into 100, that is 12.5 by 25 into 100 means 50%. So it should be changed by 50% to eliminate the wave system at the nozzle exit under steady state condition.